Section 19 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Nagami. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 13. The Earth. Part 2. Among the movements of the Earth, there is one that is so minute as to be of peculiar interest to the astronomer. It is a small displacement or wobbling of the axis of the Earth, or theoretical pole. This pole shifts its place through a circle of some few yards in diameter in the course of a period of somewhat over a year, and as a result there is a variation of latitude on the Earth's surface. This was discovered first in 1884 and 1885 by Dr. Küstner at Berlin, and after observations made at various stations by members of the International Geodetic Association in 1888, it was found that this synchronous variation was occurring in a periodic manner at a number of stations. The general nature of the occurrence was defined by Professor S. C. Chandler in 1891, who stated that the pole of the Earth might be supposed to describe a circle with a radius of 30 feet in a period of 14 months. One reason assigned for this phenomenon is a change in the distribution of mass due to the temporary occurrence of heavy falls of snow or rain limited to one continent, or to the transportation of great bodies of water and air from place to place by atmospheric or sea currents, so that the globe is made slightly lopsided and temporarily to forsake its normal axis. Also, it has been supposed that the Earth is not absolutely rigid. As a quasi-plastic mass, it would yield to certain strains, which tend to protract the time of circulation of the displaced pole. In fact, in all consideration of the various phenomena of gravitation and tides, we have to recognize that in practice the astronomer of today is not dealing with the theoretically rigid body of Newton and the earlier mathematicians. One of the important conditions of the rotation of the Earth is that it moves around an axis which is not vertical, but which is inclined toward the plane of its orbit. Dolmage, in his volume Astronomy of Today, tells us that, quote, if the axis of the Earth stood straight up, so to speak, while the Earth revolved in its orbit, the Sun would plainly keep always on a level with the equator. This is equivalent to stating that in such circumstances a person at the equator would see it rise every morning exactly in the east, pass through the zenith, that is the point directly overhead of him at midday, and set in the evening due in the west. As this would go on unchangingly at the equator every day throughout the year, it should be clear that at any particular place upon the Earth, the Sun would in these conditions always be seen to move in an unvarying manner across the sky at a certain altitude, depending upon the latitude of the place. Thus, the more north one went upon the Earth's surface, the more southerly in the sky would the Sun's path lie, while at the North Pole itself the Sun would always run round and round the horizon. Similarly, the more south one went from the equator, the more northerly would the path of the Sun lie, while at the South Pole it would be seen to skirt the horizon in the same manner as at the North Pole. The result of such an arrangement would be that each place upon the Earth would always have one unvarying climate, in which case there would not exist any of those beneficial changes of season to which we owe so much. The changes of season which we fortunately experience are due, however, to the fact that the Sun does not appear to move across the sky each day at one unvarying altitude, but is continually altering the position of its path, so that at one period of the year it passes across the sky low down, while at the other it moves high up across the heavens and is above the horizon for a much longer time. Actually, the Sun seems little by little to creep up the sky during one half of the year namely from midwinter to midsummer, and then just as gradually to slip down it again during the other half, namely from midsummer to midwinter. It will therefore be clear that every region of the Earth is much more thoroughly warmed during one portion of the year than during another, that is, when the sun's path is high in the heavens than when it is low down. Once more we find appearances exactly the contrary from the truth. The Earth is in this case the real cause of the deception, just as it was in the other cases. The sun does not actually creep slowly up the sky and then slowly dip down it again, but owing to the Earth's axis being set aslant, different regions of the Earth's surface are presented to the sun at different times. Thus, in one portion of its orbit, the northerly regions of the Earth are presented to the sun, and in the other portion, the southerly. It follows, of course, from this, that when it is summer in the northern hemisphere, it is winter in the southern, and vice versa. The fact that in consequence of this slant of the Earth's axis, the sun is for part of the year on the north side of the equator and part of the year on the south side leads to a very peculiar result. The path of the moon around the Earth is nearly on the same plane with the Earth's path around the sun. The moon, therefore, always keeps to the same regions of the sky as the sun. The slant of the Earth's axis thus regularly displaces the position of both the sun and the moon to the north and south sides of the equator respectively, in the manner we have been describing. Were the Earth, however, a perfect sphere, such change of position would not produce any effect. At present, the north pole of the heavens is quite close to a bright star in the tail of the constellation of the Little Bear, which is consequently known as the pole star, but in early Greek times it was at least 10 times as far away from this star as it is now. After some 12,000 years, the pole will point to the constellation of Lyra, and Vega, the most brilliant star in that constellation, will then be considered as the pole star. This slow twisting of the Earth is technically known as precession, or the precession of the equinoxes. We have seen that the orbit of the Earth is an ellipse, and that the sun is situated at what is called the focus, a point not in the middle of the ellipse, but rather toward one of its ends. Therefore, during the course of the year, the distance of the Earth from the sun varies. The sun, in consequence of this, is about 3 million miles nearer to us in our northern winter than it is in our northern summer, a statement which sounds somewhat paradoxical. This variation in distance, large as it appears in figures, cannot, however, be productive of much alteration in the amount of solar heat which we receive, for during the first week in January, when the distance is least, the sun only looks about 1/18 broader than at the commencement of July, when the distance is greatest. The great disparity in temperature between winter and summer depends, as we have seen, upon causes of quite another kind, and varies between such wide limits that the effects of this slight alteration in the distance of the sun from the Earth may be neglected for practical purposes." End quote. The most striking effect of gravitation in its universal aspect is seen on the Earth in the case of the tides, which are due to the attraction of the moon on the Earth, and especially on the waters of its ocean. While the ancients could not explain the cause of the daily change in the tides, the phenomenon was obvious to all mariners or those dwelling by the sea or even on great rivers. The connection of the moon with this phenomenon, it is claimed, was understood as early as 1000 B.C. by the Chinese, for at full and new moon exceptionally high tides were observed, and the name of spring tides was applied as contrasted with the minimum high water which was observed at the neap tides at the second and fourth quarters of the moon. Not only the Chinese, but the Greeks and Romans noticed this same phenomenon, and Julius Caesar in his commentaries tells us that when he was embarking his troops for Britain, the tide was high because the moon was full, while both Pliny and Aristotle connect the time of high water with the age of the moon. The connection between the moon and the tide was thus early established and practically applied by navigators, who were quick to realize the nature of the phenomenon. even though they and the astronomers were unable to present any satisfactory explanation. A general explanation of the tides as due to the disturbing action of the moon and sun, especially the former, was put forward by Newton. Newton's explanation, as described by Berry in his short History of Astronomy, was as follows: "If the Earth be regarded as made of a solid spherical nucleus covered by the ocean, then the moon attracts different parts unequally, and in particular the attraction measured by the acceleration produced on the water nearest to the moon is greater than that on the solid Earth, and that on the water farthest from the moon is less. Consequently, the water moves on the surface of the Earth, the general character of the motion being the same as if the portion of the ocean on the side toward the moon were attracted, and that on the opposite side repelled. Owing to the rotation of the Earth and the moon's motion, the moon returns to nearly the same position with respect to any place on the Earth in a period which exceeds a day by, on the average, about 50 minutes, and consequently Newton's argument showed that low tides or high tides due to the moon would follow one another at any given place at intervals equal to about half this period, or in other words, that two tides would in general occur daily, but that on each day any particular phase of the tides would occur on the average about 50 minutes later than on the preceding day, a result agreeing with the observation. Similar but smaller tides were shown by the same argument to arise from the action of the sun, and the actual tide to be due to the combination of the two. It was shown that at new and full moon the lunar and solar tides would be added together, whereas at the half moon they would tend to counteract one another, so that the observed fact of greater tides every fortnight received an explanation. A number of other peculiarities of the tides were also shown to result from the same principles." From Newton's time to the present, the tides have supplied material for astronomical and mathematical research, so that through the efforts of many astronomers and other scientists their theory and occurrence are now well understood, and the various governments make ample provision through hydrographic offices and otherwise to provide such information for mariners. In the theoretical discussion in modern times, one name stands out prominently, that of Sir George H. Darwin of England, whose researches on the tides of the Earth have developed to a point where they have a most important bearing on cosmical theory. It is desirable here to outline the chief features of tides in their everyday occurrence. The term flood tide is applied to the rising water which reaches high water mark at the moment when the tide is highest, while in falling the tide is said to ebb until low water or the lowest mark is reached. Near the times of new and full moon occur the spring tides, which are the highest tides of the month, as distinguished from the neap tides, which are the smallest, occurring when the moon is in quadrature, the relative heights of spring and neap tides being about as 7 to 4. At the time of spring tides, the interval between the corresponding tides of successive days is less than the average value of 24 hours and 51 minutes, and the tides are said to prime, the interval amounting to about 24 hours and 38 minutes, while at neap tides the interval increases to 25 hours and 6 minutes, and then the tides are said to lag. The highest tides of all occur when the new or full moon at the time the moon is in perigee, especially as this takes place about January 1st, when the Earth is nearest to the sun. Not only are the tides interesting for their relation to navigation, but on account of their intimate connection with the motion of the Earth. The daily movement of the tides is a drag on the energy of our planet and is acting to cut down its speed of rotation. If the speed of rotation of the Earth diminishes, it is obvious that our day is being lengthened, that today is longer than yesterday, and that tomorrow will be longer than today, even though these increases are all but inappreciable in the time that the human mind can fathom. Sir Robert Ball, in his Story of the Heavens, summarizes the variation wrought by the tides in the following paragraph, quote, "Let us take a glance back into the profound depths of times past and see what the tides have to tell us. If the present order of things has lasted, the day must have been shorter and shorter the farther we look back into the dim past. The day is now 24 hours, but it was once 20 hours, once 10 hours, and once 6 hours. How much farther can we go? When the 6 hours is past, we begin to approach a limit which must at some point bound our retrospect. The shorter the day, the more is the Earth bulged at the equator. The more the Earth is bulged at the equator, the greater is the strain put upon the materials of the Earth by the centrifugal force of its rotation. If the Earth were to go too fast, it would be unable to cohere together. It would separate into pieces, just as a grindstone driven too rapidly is rent asunder with violence. Here, therefore, we discern in the remote past a barrier which stops the present argument. There is a certain critical velocity, which is the greatest that the Earth could bear without risk of rupture. But the exact amount of that velocity is a question not very easy to answer. It depends on the nature of the materials of the Earth. It depends upon the temperature. It depends upon the effect of pressure and on other details not accurately known to us. An estimate of the critical velocity has, however, been made, and it has been shown mathematically that the shortest period of rotation that the Earth could have without flying into pieces is about 3 or 4 hours. The doctrine of tidal evolution has thus conducted us to the conclusion that at some inconceivably remote epoch the Earth was spinning around its axis in a period approximating to 3 or 4 hours." End quote. The existence of tides in the solid Earth as well as in the ocean was first indicated by Lord Kelvin in 1867. The first numerical estimate of the amount of the tidal oscillations of the solid Earth was made by Sir George H. Darwin in 1882, and was based on an indirect method and resulted from observation of the tides of the ocean. Further indirect methods were successfully applied later with more complete data. Sir George H. Darwin has expressed the opinion that we may now feel confident that the Earth yields to the tidal forces to the same degree as would a steel globe. The amazing accuracy of Dr. Hecker's recent observations, 1908, are marked by certain collateral considerations, among which may be mentioned the flexure of coastlines due to the varying pressure of oceanic tides, and the effects of high and low barometric pressure in bending the Earth's surface. It is impossible to give an accurate measurement of the amount of the vertical motion of the Earth's surface, but it is probable that at spring tides in this latitude the surface of the solid Earth moves up and down through about 6 inches. End of section 19.